Good evening, everyone. My name is Udeshka Vijayaratna, or Udi. I'm the Alumni Engagement Manager for the Faculty of Science. Let me start off by acknowledging the traditional owners of this land, and let me pay respects to their elders past, present, and future. I'm delighted today to kick off our first Alumni Science webinar with the School of Mathematics, and to welcome all our alumni and stakeholders joining us this evening. So huge warm welcome, and thanks for joining us at a quite late hour for Australians, but of course we've got other alumni who are joining us internationally, which is at a much earlier time for them. Our community is about 40,000 alumni strong and spread about in 85 different countries, which means that doing these virtual events is a great opportunity for us to connect not only with our local alumni, but also with our international alumni. And in terms of the latest research and the work that's happening in our various schools, it's a great opportunity for us to share that with you and keep your learning and development ongoing as alumni of Monash Science. As you may or may not know, the Faculty of Science has 5 different schools: the School of Biology, the School of Mathematics, the School of Chemistry, the School of Earth, Atmosphere, and Environment, and the School of Physics. So we've got alumni from all these variety of areas of pure sciences, and hopefully through these webinars we are able to bring to you research from all the different areas from the various schools. So without taking further time, I'd like to go into the format of today's event. So you'd hear from the head of School of Mathematics, Professor Warwick Tucker, who will talk to you about his vision for the school. And we've got our amazing Associate Professor Burkard, who's going to talk on the topic for about half an hour for the webinar, and then about 15 to 20 minutes after 8:40 for questions and answers. So any questions you've got, I would encourage you to put it in the question Q&A section just below the image for your video. And at the end of the session, Burkard will actually answer those questions. So let me introduce you to our MC for this evening, Professor Warwick Tucker, who is the head of School of Mathematics. He has joined us in the year 2000 and joining us from Uppsala in Sweden. He's been the head of department for about 5 years there. Look, Professor Tucker is Australian born. However, before coming back here, he's had numerous international experience where he's worked with IMPA Brazil, Cornell University in the US, and University of Bergen in Norway, and INS Lyon in France. His areas of expertise, or what he does or works on, is in dynamic systems and stochastic systems, and also in computational mathematics. His work's world-renowned, and obviously, which he's done publications in very many impact journals. He's won many awards for his achievements, and this includes the Swedish Mathematical Society's Wallenberg Prize in 2001, the Moore Prize for Applications of Interval Analysis in 2002, and the European Mathematical Society's Prize for Distinguished Contributions in 2004 for his contribution to mathematics. So we are very excited to have him join us at Monash Science, and I'd like for him to share with you his mission and where he would like to take the School of Mathematics through his experience, changing the way we teach and incorporating new things. So I'll leave it with you, Professor Tucker.
It sounds very impressive when you put it that way. I assure you who are listening, it is not. What is impressive, however, is the School of Mathematics at Monash University. This school consists of 40 academic teaching and research staff, roughly 15 postdocs. We usually have more, but as you know, it's been very hard to recruit on the international arena lately. We have over 50 PhD students who are driving our research frenetically. We have a handful of administrators that take very, very good care of us and make sure that we stay on track. And we have a myriad of sessionals who help us during the semester with our tutoring and marking of exams. So as a school, we sit in the Faculty of Science, and that is very appropriate because mathematics is the language of science. Everyone has to know mathematics to do science. And as such, we do a lot of teaching, which we call service teaching, into the faculty. In fact, every year, 10,000 students take one or several of the 70 units that we offer. That's 10,000 students that learn something about mathematics at our school. And now this is not only within our faculty, of course. We teach into engineering, into IT, into business and economy. Mathematics is everywhere, right? And of course, we teach our own mathematicians. So almost 200 students graduated last year with a specialization in mathematics. And that's an increase of 50% since 2014. So I think it's very healthy numbers. Apart from teaching, of course, we spend a lot of our time doing research. We do research in all kinds of areas, in pure mathematics, which includes combinatorics, graph theory, algebra, topology. We also do research in applied and computational maths, which includes optimization, numerical methods, mathematical modeling, which has proved so important in the last year. And we also have a group working in stochastic processes, which includes probability, mathematical statistics, and mathematical finance. We also have a few centers attached to our school. One is the Monash Center for Quantitative Finance, where they develop very advanced methods for mathematical finance. Another one is Matrix, which is a residential research institute for Australian mathematics. This was founded by us and the University of Melbourne in 2015, and last year ANU joined us as a full partner. Matrix provides international research programs, online seminars, PhD student symposia, and they also have their own book series. But what is it we think about when we do mathematical research nowadays? Well, the answer is almost everything. Just to give you a little taste of this, this year our staff put forward 24 discovery project applications to the Australian Research Council. And I just want to read a few of the titles of these applications to give you a little feel of what we're doing here. One is Optimal Shapes in Geometry and Physics by Julie Clutterbuck. Here she's looking at the interaction between geometry and physics. The classical question in this area is, can you hear the shape of a drum? And the answer is sometimes, sometimes not. And she's kind of pushing the frontiers in this direction. Another project is titled, Can Green Investors Drive the Transition to Low Emissions Economy by Ivan Guo. This is from financial mathematics, and it's stochastic game theory under the hood, looking at different actors on a market with different agendas. A third one is Machine Learning Applications for Space Weather Predictions by Alina Dunia. So she's trying to predict the weather in our planetary system, in particular, when do solar eruptions occur? Because knowing this helps us protect the sensitive equipment on our satellites around the Earth. Now, that's just a little bit. We had 24 different applications. There were many more projects going on within the school. Taking a step back to the Faculty of Science again, if you think of a scientist, you think of big labs, field trips, expensive equipment. Well, it doesn't quite look like that in mathematics. Instead of big labs, we have our brains. Instead of field trips, we have our thoughts. And instead of expensive equipment, we invest in people, that is, in mathematicians. And one such mathematician is our speaker tonight. This is Associate Professor Burkard Polster that I'm happy to introduce to you now. Burkard earned his PhD in mathematics in 1993 from the University of Erlangen-Nuremberg. And as many mathematicians, you travel around the world and do kind of different jobs and learn the ropes. So he has held positions at the University of Würzburg, University of Albany, University of Kiel, University of California, Berkeley, University of Canterbury, University of Adelaide, and in 2000, Monash struck gold and he came to Monash University. He's the author of at least 9 books, and this morning I counted 77 videos posted on his YouTube page for Mathologer, where he explains the joy of mathematics to the general audience. Behind all of this, or beyond all of this, Burkard is also the Director of Undergraduate Education within our school. So thanks to him, 10,000 students get a piece of the mathematics action every year. And now we're going to get a piece of that action too. And Burkard will tell us what mathematics and YouTube have in common. Please, Burkard.
Oh, all right. Well, since you're watching this, I guess you're interested in mathematics or YouTube. Well, let me tell you about both from the perspective of someone who does a lot of both, the Mathologer. I'm here today as the Mathologer, someone who wears fun maths t-shirts and talks about cool maths on YouTube. So let's jump straight in, okay? Let me share this screen. Here we go. All right. Okay, so this is the front page of the Mathologer channel. And let's just have a look at some statistics to start with. So the channel started in 2015. And then what everybody's interested in is subscriber numbers. Okay, subscriber numbers kind of goes up by 100,000 every year. Last year in August, we were at 600,000. At the moment, we're at 680,000. So if I keep doing this for a couple more years, it will be 1 million. It will be very, very exciting. Who's watching this? Well, there's a lot of people from America who watch this. Then there's people from the UK, India, Germany. Why Germany? Well, you may have picked my accent. I'm not originally from here. I'm from Germany, and I mean, all the people from Germany get my jokes, so that's why they're watching my channel. And then there's Canada. And where's Australia? Well, actually, Australia is next with 3.2%. Used to be in 5th place, but then India discovered Mathologer and displaced Australia and a couple of other people. Anyway, so that's about 22,000 subscribers here in Australia. Okay, then we've got age profile. It's about this. So who am I targeting these math videos to? These are mostly people who are intrigued by mathematics, who are interested in mathematics, who do not necessarily have a very strong mathematical background. So you don't have to be a PhD in mathematics to watch these videos. So if somebody's, for example, in high school doing maths methods and is really enthusiastic about, solving puzzles, they can enjoy whatever I'm doing on the channel, I hope. And this is something that surprises a lot of people. So there's a lot of news always about male-female ratio in schools, at university, have a look at YouTube. So we've got 94.2% male here. And this is not just Mathologer. I mean, I'm speaking about pretty much across all YouTube channels that deal with mathematics, at least the sort of mathematics that I'm doing. There's a school-oriented mathematics like Khan Academy or a couple of other ones. There's people there who want to learn something. The ratio there is a little bit different from this one. Now, what does Mathologer do? Well, when I started out, there was one YouTube channel, sort of the pioneering mathematics YouTube channel, Numberphile, and they did, fun maths, numbers, mostly entertainment, but quite a bit of maths in there too. So when I started, I wanted to be a bit more substantial. I'm still entertaining, as accessible as possible, but more substance. So really do the maths as best as I can and as accessible as I can. And over the years, that has developed into more and more sort of hardcore things. So these days, a lot of the topics that are being covered here are really milestones of mathematics that you would only really encounter in depth in higher level maths units at uni. So, I mean, if you just have a look at a couple of titles here, for example, quadratic reciprocity or Fermat's two-square theorem, or this one, for example, let's just have a look at this one here. It's 2,000 years unsolved. So this has been going on for 2,000 years, right? And so the ambition here is to really contribute something to this 2,000-year history of this topic. So lots of people have been thinking about this, have been researching this. And so what we want to try to do in the channel is present the most accessible introduction to this topic. So what is this about? Well, it goes back to ancient Greece, the Greeks. They were really interested in doing everything in the simplest possible way. So what can you do? What mathematics can you do with just drawing circles and drawing lines, ruler and compass constructions? That's what we were interested in. So just give you an example here. So it's an angle here, and we want to bisect it. And we can do this with circles and lines, ruler and compass. So we draw a circle here that gives us 2 points of intersection there and there. And then we draw 2 circles, same radius, one here and another one here, same radius, right? That gives another point of intersection up there. And now you can put a line through this, and that line bisects the angle. You can do lots and lots and lots of things with just ruler and compass. I mean, it sounds very simple, right? There's hardly anything there, but it's incredibly powerful, this little toolkit that the Greeks gave themselves there. So for example, what you can do is you can start with 2 points, maybe a unit apart, and then with ruler and compass, you just go kind of wild, drawing circles and lines. You can make up a square, okay? And once you've got a square, you've also got the diagonal of the square, and that's square root of 2 long, so you've constructed the number square root of 2. Now, they've tried all sorts of things, but with some of them, they really hit some obstacles. They couldn't do it. So one of them is a very famous one. It's called doubling the cube. So again, you start with 2 points a unit apart. And then again, you want to go wild with ruler and compass and construct all kinds of new points there. And somewhere in this cloud of points that you're constructing here, you want to find the distance of cube root of 2. And that has to do with doubling a cube. So if we take the cube with side length 1, then a cube with side length cube root of 2 is just double the volume of the one that we started with. So that's, you know, it's something to do with a story about a plague that had to be somehow subdued, and you have to, you know, give something to Apollo, and that means you have to double the cubic altar. Anyway, something like this. It's doubling the cube, and they really couldn't do it. They really couldn't do it. And there were a couple of other really famous things they couldn't do, like squaring the circle, which you may have heard of. Anyway, so this goes on for hundreds of years, well, really 1,000 and something years, until in 1830, somebody, a French mathematician, figured out how to solve this. And he figured out that you can actually not construct the cube root of 2, no matter how hard you try. You can't square a circle. You just can't do it, right? And it's amazing. I mean, it's amazing. And of course, when I went to uni, I learned about this. But where do you learn about these things? It's in a unit called Galois theory. And it's in maybe 3rd year or honors year or even later. Some people never hear about these things. That's where you hear about it in depth. That's where you hear about the proof. That's how you hear about the real argument, the beautiful argument for why this can't be done. And so in this video, what we're really trying to do there is take this really deep mathematics, kind of take it apart, take anything that's really been good, that's been said about it, any good argument, anything that's clear, and kind of reassemble all this into something new, into something that is accessible to, well, for example, my high school student who's really interested in puzzles, doing methods at the moment in school. That high school student is supposed to understand this argument. So can this be done? It can be done if you just try really hard. I mean, people always say a picture is worth 1,000 words. Well, a video or an animation or a combination of all those things combined with all kinds of other things is worth 1,000,000 words, or can be worth 1,000,000 words. So I mean, just have a look at the numbers here. This is about really, you know, tough, pure mathematics. It's got almost 1,000,000 views. I mean, when you see these numbers, you've got to be careful, right? It's like 1,000,000 people, not all of those will have understood what's going on here. A lot of they are just there for the flashing lights and the colors and the entertainment. But a substantial number of these people who view these videos actually really get it. And then we kind of look back over this 1,000-year history of, you know, rule and compass constructions. You have that many people who really understood the solution, who really understood the proof, up to the day when this video goes live. And then a year later, it's probably 10 times, 20 times the number of people who now understand what's going on there. And that's just amazing what's possible there. So just in terms of numbers, so the most viewed video at the moment is this one here. It's actually already 4 years old. It's almost 4 million views. So that's, in Australia, it's about 120,000 people who would have watched this. And what that means, just for example, for me, is when I kind of walk through the city, there's people coming up to me and asking me, are you the Mathologer? Can I take a selfie with you? And not only in Australia, I mean, like across the world, right? You travel, you're somewhere in Japan and you look at a temple and somebody comes up to you and wants to take a selfie with you. It's, I mean, I don't get paparazzi. That's what happens. Okay, so this is again a piece of mathematics. It's really about the Riemann rearrangement theorem, which is something very paradoxical. When you learn in school that 2 + 3 is equal to 3 + 2, or really like add any bunch of numbers, right? 1 + 2 + 3 is the same as 3 + 2 + 1 is the same as 1 + 3 + 2. Permute them any way you want, you always get 6, right? Always the same sum. It doesn't matter how you jumble them up, it's always going to be 6. Now with infinite sums, things change. For some infinite sums, it actually happens that the sum changes when you permute the terms. Something very counterintuitive, and it's explained in this video with sort of visual algebra. So at the end of this, I'm actually going to show you how this is done, okay? And then you got an idea of you know, the general approach in the channel. All right. Okay, so one really big aim at the moment is really kind of take these milestones of mathematics, something that's fairly deep, and really give it, you know, a best shot to get this in a format that our target audience can stomach. I mean, sometimes it just doesn't work. I mean, it's just too hard, and we try, and in the end, yeah, the people with a really solid background, they get it, but then we sort of miss the target a little bit. But in general, I think it works out quite well. Okay, now, there's something else that is really always on our minds when we do these sorts of things, and that has to do with this guy here. I don't know whether anybody is familiar with this person. Who is he? Well, for my generation, he was probably the most influential person in terms of getting people interested in becoming mathematicians by a long stretch. So his name is Martin Gardner. And the most remarkable thing here is perhaps that he was not a mathematician at all. So he was a journalist. He was somebody who was interested in performing magic tricks. He was interested in debunking psychics. He was interested in origami. He was interested in all sorts of things. And what happened at some point in time is he got an offer from the editor of the Scientific American publication, to write something about origami, which was sort of mathematical, about Flexagons. And that went viral. This ages ago. I mean, I'm actually quite old. So that went viral. So it's about these funny things. Actually, I'm going to just quickly stop sharing here to show you one of these things. So that's a Flexagon. Let's see whether we can get this in focus. Okay, that's good. So it's got two sides. There's a blue side and there's a black side. But when I manipulate this a little bit, I actually also got a red side, which is strange, right? So it's magical. So this went viral, and actually you can make these things to have many more sides. You can have them to have usually 6 sides, or you can have 20, you can have 100 if you just go big enough. So this went completely viral, and all sorts of people got to know about this. And well, I mean, maybe you're interested in this construct here. Let's see. So that's a Möbius strip. So what I just showed you, this flexagon, is actually just a Möbius strip in disguise. And once you got Möbius strips, you're actually not too far away from research into the shape of the universe. So it's sort of all connected. And eventually Martin Gardner wrote about all these things. So let's just go back to sharing my screen here. Okay, so what else did he make popular? So there's, oh, dragon curve, right? Oh, I better myself there too. So for that one, you need a strip of paper. Okay, so a strip of paper, and you just fold it once, you fold it twice, and you fold it 4 times. And in fact, what you have to do is you have to imagine you fold this infinitely often, and then you unfold it like this. And I'm gonna have to kind of move back and forth in front of my face a little bit to show this to you. So what you get here is a little figure that looks a little bit like a dragon. So there's a kind of a face here in front of my face, and then there's 2 little legs where I'm holding it, and there's also a little tail there in the back. Not that clear to see, but if you just do it, like just take a piece of paper and kind of fold always in one direction, you just keep on going, and then you unfold the whole thing, and then what you get is something that looks more and more like a dragon. This dragon here. And that's got all this self-similarity built in. So if you kind of zoom in, you see the whole dragon repeating over and over again. And there's the Mandelbrot set and all these sorts of things coming in. I still remember being absolutely fascinated by these things when I came across Martin Gardner's columns. And you know, the first thing I probably programmed was this dragon here. So 12 times folding, you know, this really primitive machines that we had at the time, you know, make up this thing. So incredibly. We've got something here in Melbourne that's also been made popular initially by Martin Gardner. It's the Penrose tiling. So Roger Penrose, of course, a very famous mathematician and physicist. So he invented this strange tiling based on these 2 tiles here, which you can admire on Story Hall in Melbourne. And you know, I'll say what it is. You can tile the plane in a non-periodic way with these 2 tiles. On the other hand, no matter how hard you try, you can't tile it in a periodic way, in a nice repeating way. So only mess is possible, nothing nice is possible, which is very remarkable in some ways. Anyway, there's other things that Roger Penrose is famous for and that Martin Gardner popularized. For example, this diagram on my t-shirt here, that's an impossible triangle, right? So you can see this is completely impossible. And then you may have seen these in the works of M.C. Escher. Escher would probably not be famous at all if it hadn't been for Martin Gardner, including his paintings and sketches in his publications. So I'm sure you've heard of some of these things at some point in time. So hugely influential. He had this network of collaborators who would feed him stories, and you know, he wasn't a mathematician, so he had to first kind of explain this to himself, but really to kind of take it apart for himself, explain it to himself, and then explain it to others. And that worked incredibly well. And as I said, I mean, I was, you know, just so taken by all this. This is mathematics. I want to be a mathematician. But when I actually really got into mathematics, that was just research. When I came to Monash, I was here on a research fellowship. Then I met somebody, Marty Ross. He was here already. He was also one of those guys who was basically influenced by Martin Gardner to become a mathematician. So we hooked up and we got a gig with the Age here in Melbourne to write a mathematical column for the Education Age. And that went on for quite a while, from 2007 to 2014, about 260 articles. It was a lot of fun. And really got us going in terms of following in Martin Gardner's footsteps. At the same time, like even before I came here, Marty had started something here at Monash, which is still going on. He's left in the meantime, he's sort of retired. But I'm still going, and it's a unit, it's a very special unit, which I think is unique to Monash. It's called The Nature and Beauty of Mathematics. And actually it's on again next week. So next week on Tuesday, what will I be doing? Well, there will be about 220 students, I think last time I counted. And I'll tell them about visualizing the 4th dimension, mathematical soul capturing, the maths of juggling and lacing shoes, optimal design with soap bubbles, minimal networks, Fibonacci numbers and golden ratio, shape of the space, the Möbius band, Möbius strip stuff, and lots of infinity, pi, all of these things. And it's going to be students from across the university, from arts, from medicine, and all of these people, I mean, they may not have a very strong mathematical background, but they're all intrigued. They want to find out about these things. And inherently, mathematics is so beautiful, so deep, so it's just amazing. It's just that most of the time in school, you don't get this at all, right? So you don't get what drives us, what drives the mathematicians. And so this is what this unit is about. And it's just a great thing that we have it here at Monash. And just in general, kind of the support for the sort of things that I'm doing here is just phenomenal. All right, now, why do 4 million people want to watch this video? Well, there's a bit of a Simpsons hook, and then of course, I mean, you read pi is equal to infinity minus infinity, and you really want to click this, I think. But it wasn't that easy. If it was that easy, I would have more videos like this. So a lot of luck there too. But let me just explain to you this whole business about infinite sums can be rearranged so that the sum changes. Okay, so first of all, we need infinite sum. We actually say, we call this thing a series, an infinite series, okay? So this infinite series has infinitely many terms, and these are just the reciprocals of the powers of 2. I just want to explain to you what actually the sum of this is, right? It's not clear at all. I mean, there's a monster, right? Infinitely many terms. So what's the sum of something like this? Well, you just start adding, right? So 1/2 plus 1/4 plus 1/8, and you kind of note down the sum underneath, right? And that gets you the sequence of what we call partial sums. When you have a look at it, well, I mean, you definitely see a pattern here, right? So here at the bottom, you've got the powers of 2, of course, and then at the top, it's just always one less, right? And the numbers go bigger and bigger, so clear pattern. And so what number do we see here after a while? What number we see here after a while? Well, these fractions get closer and closer to 1. So the sequence of numbers, the sequence of partial sum converges to 1. Okay, so it converges to 1. And what that means then is for us mathematicians to say that the sum of the infinite series is equal to 1. So for an infinite series to have a sum, that just means that the sequence of partial sums converges to a number. Okay, that's what it means. So now we've made sense of an infinite sum to start with. Okay, now let me show you another sum, which is very, very famous. So instead of just doing the reciprocals of the powers of 2, I'm going to do the reciprocals of all positive integers, right? 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. Obviously, the reciprocals of the powers of 2 are in there, so this will be somehow bigger. How much bigger? Well, let's just go, right? Partial sums, there, it's this. Have a look at the pattern. Ooh, it looks pretty awful. It's a mess, right? It's a mess, but you know, just have a look at it and see what happens. And what happens is that actually this sum doesn't settle down. It doesn't converge. It actually explodes. It explodes to infinity. So these fractions there, they're not bounded, right? They go bigger and bigger and bigger and bigger. And if you want a sum there that's a trillion or a Googleplex, you can get it. You just have to keep adding. You'll get to any number as big as you like. And actually, this has been known since the 14th century. There's a really brilliant proof there by a French bishop. But I'm not going to talk about this. So I just want to fix this sort of in your mind as a kind of a starting point. Okay, so now you know what it means for infinite sum, what it means for an infinite series to have a sum, and you also know that this particular guy here diverges to infinity. All right. Now what we want is, we want one of those special series that can be rearranged to give different sums. So for that, we need some minus in here. So what we do is we change every second plus into a minus. Okay, so every second plus one. And then we play the same game again, right? We just do partial sums and just see, does this go to a number? Does this converge to some number? And this one does. It's actually a very nice number. It's the natural logarithm of 2, which is about 0.7. Okay, pretty. I mean, just by itself, it's really, really pretty, right? So now, what I'm saying is that this particular sum here, if you rearrange the terms, you can make the sum of this rearranged series to be whatever you like. If you want it to be pi, fine. If you want it to be square root of 2, fine. If you want it to be minus infinity, I can do this. If you want it to be plus infinity, I can do this. If I wanted to jump around like crazy and not settle down to anything, I can do this. And what I want to show to you now is how this is done, what the proof. Basically, there's Riemann's rearrangement theorem, which says that. And then there's the proof. And now what I want to show you is kind of visual algebra, which I hope you'll be able to appreciate, right? So you'll be able to see the proof, you'll be able to appreciate the proof, which usually, I mean, I do it in actually another unit I'll be teaching this semester in MTH 103 in about 6 weeks' time, I think. Okay, so we take this series apart into all the bits that are positive and all the bits that are negative. So if you now focus on this one, what does this add up to? Well, it actually still adds up to infinity. The other one to minus infinity. That's kind of interesting. Is that clear? It's sort of clear, at least for this one here. Just remember, this one was the original sum, right? Or original series. That sums to infinity. Now we just kind of divide everything by 2. 1 by 2 gives 1/2. 1/2 divided by 2 gives 1/4. 1/3. So you basically take this guy divided by 2, infinity divided by infinity is still infinity. So it's pretty clear that this will be minus infinity. Then I think you also believe that this one's positive infinity, right? So believable. All right. Now, what that means in some way is that this natural logarithm of 2 is infinity minus infinity. Okay. Now what I want to do is I want to rearrange those terms. I want to jumble them up and I want to get pi. I want a series that adds up to pi. How am I going to do this? Well, there's pi, 3.1415, and so on, right? So what we'll do is we'll start out with the positive terms and just keep adding, okay? So 1 plus, that's 1, okay? Plus this one, plus that one. And we just keep on going until we get closer to pi, okay? So there. So we're still not quite there, okay? So we just keep on going one more term. Now we're actually over, all right? And so now that piece of the first series, we're going to take as the starting for the target series that we're aiming for, okay? So we're going to take this here, all right? And, all right, bring back the rest. Now, what does this add up to? Well, think about it. Well, this was infinity to start with. Now, this is a little bit like 3.14. So we're just taking away that one from infinity. So that's still infinity, okay? Now we're over, right? And we're going to go under pi now. So for that, we need the minus guys. So we're just going to add this minus 1/2. And that actually gets us under again. Now we're going to get over again. And for that, well, let's just kind of go back. So nothing much has changed. It's still minus infinity here, right? Now we go take positive terms until we're over again. Okay, so let's just do this. Okay, keep on adding. At this point in time, when we add 1/409, we're just over pi. And then we go backwards again, right? So we can just take another term here. It's still infinity on top. It's still infinity at the bottom. And actually, that stays the same throughout. You know, at any point of this construction here, you've got infinity on top and minus infinity at the bottom. Although things get less and less. It's also a bit weird, right? But that's what it is, right? And the other thing that happens is that these fractions that you see here get smaller and smaller. Right? So we're kind of going over pi and then under, over, under, over, under. But because these things get smaller and smaller, the oscillation around pi gets smaller and smaller. What's also clear that eventually we come across any single one of them. Right? So I mean, we can take 1 Googleplex. Eventually, we'll have to include this in here. Right? So eventually, when we're kind of finished with this whole construction, we actually do get a sum or a series that sums to pi, exactly. And we can do the same sort of thing here for any other number whatsoever. Right? And that is the essence of the proof of the Riemann rearrangement theorem. I hope you you like this, okay? Okay, and actually you rearrange this series in infinitely many ways to get the sum of pi. All right, just quickly, how is all this done? Actually, for the most part, what I'm doing here is I'm animating letters, right? They kind of fly around on the page. And what I'm doing here is most of the time just work in the counterpart of PowerPoint for Apple. That's Apple Keynote. So this animation that you've just seen here, that was done in Apple Keynote. I also use other more specialized pieces of software to do my animations. So for example, this one here is done in Mathematica. Anyway, I think my time is pretty much up for what I'm supposed to say, half an hour. So I think I'll finish here and hand back to Warwick. And stop sharing.
Thank you very much, Burkard, for that lucid presentation. I think we have a couple of questions from the audience to you, if you're prepared.
I'm prepared.
Okay, so Linda is wondering, let's see if I can read this. Your YouTube examples don't seem to include applied math areas such as fluid dynamics and how they influence practical issues and so forth.
Yeah.
Yeah. Is that because the math is too complicated to explain to a general audience?
Well, partly it's personal preference. I mean, I kind of started out as a pure mathematician, so I've got a bit of a pure bent there. But there's actually, I mean, if you look at, I mean, through the list, there's actually quite a few things. So I mean, I might talk about, you know, the best way to lace your shoes, and that may seem like it's got nothing to do with anything, but actually the maths that underlies everything that I'm doing there is highly applicable. So that goes into things like the traveling salesman problem, which is, you know, done everywhere where you kind of optimize. You kind of fly around the planet, right? You want to plan your trip so that it's kind of shortest, right? You want to go to Berlin, and then you want to go to Nicaragua, and then you want to go there. So how do you plan your trip so that the overall trip is shortest possible? So the maths that goes into these sorts of planning is exactly the same sort of maths that goes into figuring out what the shortest way to lace your shoes is. So we've got, you know, lots of examples of these sorts of things. Yeah.
Yeah. Okay. Another question from the audience is, okay, this is a tough one. Which of the remaining clay prize problems do you think are solvable?
Well, all of them. It just depends on how long it's going to take.
Okay. Okay. So we still have some work ahead to do.
Yes. Hope.
Another question, more practical one, is do you create your own animations? If yes, how? If no, then who makes them for you?
Yeah, so pretty much I do everything myself these days. So I do all the animations myself. I do all the filming myself. I do the subtitles myself. I don't know. The logos, everything is pretty much done myself. But I've had some helpers. So what I'll really do is I've pass it by a couple of people for proofreading feedback. So for example, Marty, the person who kind of started the unit at Monash, he's still very much active in the background. So when I'm done with the script, I give it to him, and then we have, you know, fights over these things to get the wording right. But apart from that, it's, yeah, I'm really quite keen on graphic design also. I mean, I've spent a huge amount of time doing these things. So it's basically like knitting a Persian carpet, right? It's the individual frames are, you know, pretty straightforward, but you have to have like hundreds of them. So the slideshow for one of these YouTube videos can be up to, you know, 500, 600 individual slides. It's basically animation, right? And it takes a long time. Of course, you're kind of getting good at it after a while. And as I said, I mean, most of them are really quite doable for anybody. So if you've got access to something like Apple Keynote, there's a feature called Magic Moves. And what you put in there is basically 2 frames. And then the software automatically does the transition for you. You've got to be a bit smart to get the effect that you want. But, you know, I mean, just have a look at the videos and see how the equations fly around. And that's all done in Apple Keynote.
Okay, fantastic. Another question. Are there any recent mathematics works that make it into your videos? You've talked about ancient mathematics, but do you also kind of incorporate modern mathematics into your videos?
Yeah, absolutely. So, I mean, not the last video, but the video before that, that's maybe 10 years old. So it's called something about the Arctic theorem. Very strange one. Really very bizarre kind of effect. You know what a domino is, right? You take a domino and you tile a chessboard with dominoes. You can do this in many different ways. But then if you chop up the chessboard to look like a diamond and you tile it with dominoes in a random way, then all of a sudden some circle starts appearing out of nowhere. It's really bizarre. And so that's what the Arctic circle theorem is about, and what this video is about. So maybe check that one out. Yeah,
Okay.
and other recent pieces of mathematics, they feature, yeah.
Great. We have a question about the infinite sum of series that you showed. It didn't look like there was a nice way to write it. Is there a nice way to write these kind of sums, or are they messy in general?
They're pretty messy. Well, I mean, having said that, I mean, there's so many really pretty ones. I mean, just imagine the one that I kind of started out with, right? This natural logarithm of 2, right? It's 1 minus 1/2 plus 1/3. I mean, it's completely, there's other ones for pi, for example. Pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1. These are really, really pretty. I mean, so you can get really nice pattern there. I mean, much, much nicer than the decimal expansion of pi would suggest. I mean, that's a complete mess, right? But in terms of these infinite expressions, you take anything famous like pi or e or golden ratio, or anything like that. There's, you know, infinite expression with lots of amazing patterns in them that, you know, you really boggle your mind.
Yeah. My favorite is pi squared over 6.
Yes.
Here's another question for you. Is there a lot of mathematical misinformation on YouTube? We hear about fake news daily, but
Yeah.
is there something similar for mathematics on YouTube?
Yes, absolutely. I mean, there's a lot of garbage on YouTube, and that includes mathematics. So, I mean, you got to be very careful on YouTube where you go. So don't believe everything that people say. So even if the channel is big, doesn't mean that what they're saying is very good.
And here's a difficult question for you, Burkard. So you've shown us some of your really fantastic videos, but do you have, could you share an example of a video idea that really didn't work out so well? And can you explain why you think it didn't work?
Let's see, which one? Well, in terms of the target audience, maybe. So there's this one question which is also ancient, which is, I mean, to start with, is pi irrational? So pi, you all know pi, right? But can you actually write pi as a fraction, like, you know, 22 over 7? I mean, everybody kind of gets this in school, and actually some school books sell this as the true value of pi, believe it or not. It's not, right? And you know, you can get arbitrarily close with fractions to pi, but the question is there one fraction, like integer on top, integer at the bottom, that is pi? And there's proofs that say it's not, but they're very, very hard. I mean, really, really technical. And then one step up from that is pi transcendental? So that's about, you know, polynomials like x squared plus 5x minus 7 equals to 0. Can pi be a solution to that? You know, you can really make up really, really complicated ones with x to the power of 666, whatever, right? So just anything you can imagine with integer coefficients. Can any of those give a solution that is exactly pi? And the answer is no, cannot. No matter what you try, pi cannot be represented like this, and which means that pi is transcendental. And so Martin and I, we really wanted to do one of the proofs there. I mean, it's just, I mean, everybody told us you're absolutely out of your mind to even try this. But we did it anyway. And that took forever. I mean, I'm pretty sure we took like 200 hours to just like look at all the proofs, find the one that's kind of closest to being mathologerized, and took it apart, redone it, all kinds of things. I mean, overall, we're very happy with the outcome, but definitely my year 12 guy with interest in puzzles, maybe not. But at the same time, I mean, it's working very well for some people for people with a little bit more mathematical background, right? So if you've maybe had like a year of, or maybe a semester even of maths at university, you'll be able to get something out of this. But you know, we just couldn't do it.
Okay. Here's another question from someone with zero math background. Have you ever done a YouTube video to go through all the proofs in Good Will Hunting?
Haven't done a video, but I've written a book.
Okay, can you tell us about that book?
Yeah, it's called Maths Goes to the Movies, and it's again with Marty. So we've got a bit of an obsession about collecting maths in the movies. So we've actually also the authors of the Mathematical Movie Database, the MMDB. So you can look this up on the net. So it's got thousands of entries there where you can find mathematics. And at some point in time, we actually wrote a whole book about maths in the movies. And Good Will Hunting has a whole chapter in that. So we took the whole thing apart, and actually we did an interview with the person who did the maths consulting. So if you want to know about Good Will Hunting and the maths, it's all there. And actually, I'm pretty sure the part about Good Will Hunting is you can get it for free on Google Books. So there's a preview of the book. So if you just go there and just list around a little bit, there should be the Good Will Hunting chapter. Well, actually, I'm not sure now whether it's the Beautiful Mind chapter. I'm pretty sure it's the Good Will Hunting chapter.
Ah, what a shame. I would have preferred the Beautiful Mind. But
well, I mean, you can just come to my office. I'll give you the book.
Yes. Another question for you, Burkard. Has your work on YouTube influenced your teaching or research?
Well, to be honest, this work on YouTube pretty much takes up all my time. Apart from what I do here as my daytime job and family, I've got 2 kids, right, who need to be taught how to drive cars, for example, and how to do maths in school and all these sorts of things. Apart from that, it's the channel, and that's it, right? But as I said, I mean, it's really quite ambitious what we're doing here. We're really contributing to to things like circle and compass construction. So I mean, I don't really feel bad in terms of not doing terribly much original research, but rather trying to explain things in the best possible way. So that's sort of my calling, I think. And I think I'm going to stick with that even when I'm retired, that's going to be it. So you still see me doing maths videos.
Yeah. And on that thread, I mean, many people don't understand even the simple concepts of, for instance, independent events in probability, like statistics. And this, of course, can have a real-world consequence in their lives. How do you think we can improve their understanding, I mean, in the broad general population?
Well, definitely YouTube is a very good channel. And I mean, just in terms of statistics, there's actually a few colleagues here who've done really, really nice videos, and they're very popular. And not only mathematicians, there's a couple of other ones who are really, really, really popular. For example, Veritasium. That's a guy also originally from Australia. He does all sorts of science-based stuff, but a lot of it, very popular, is about statistics. And I'm sure he's had a huge impact on people getting a better understanding of what it all means.
Okay, and now, unfortunately, we've come to the last question for this evening. Let's see, if students, I mean high school students, were taught maths the way you teach it, there would be a lot more students interested in pursuing mathematics. YouTube is a great way to teach them, but do you think there is something else that can create this connection and interest?
Well, I mean, the YouTube is very good, but I mean, one thing you should not forget is that in the end, you have to do the maths yourself to really get proficient at it. There's no real shortcut to doing the work, really doing exercises over and over and over. I did this in school, and if I hadn't done it, even if I had access to YouTube, I would not be a mathematician at the moment. So you can, I mean, definitely YouTube, what we're doing here, the topics, the way we present it, that should be part of what people do in school, no doubt. But at the same time, you really have to do the work. Everybody has to do the work. And actually, one of the problems of YouTube at the moment is that we are getting students who are very, very interested in mathematics, but they can't do the maths. So when they come here, they say, yeah, I know everything about transfinite induction because I've watched this YouTube video, but they can't solve quadratic equations. And then, but if you can't solve quadratic equations, then that won't help you to actually really understand things beyond what somebody does for you on YouTube.
Yeah. It's like learning an instrument. You really have to do it yourself.
Yeah, you have to do it yourself. Yeah.
So thank you again, Burkard, and I'll hand over to Udi now.
Yes, look, thank you, Burkard. It was quite an interesting presentation, and thank you, Warwick, for your time. Look, I thank everyone who's actually joined in. They were quite interesting, questions and difficult questions. So thank you for answering them, Burkard, and thank you all for attending. At the end of this presentation, over the next couple of days, I will send out the recording of this webinar. So if you want to, share it, or if you want to listen to it again, you can certainly do so. And look, I mean, the only way we can improve these events is that if you do give us feedback, and we can, I think, like, we're going to continue to do similar events for our alumni. And if there's any feedback to improve, certainly do say it. So I'll send a feedback survey, so I would appreciate if everyone could fill it out for us. So thank you. It was a great evening. Thanks for joining us. And if there's any questions afterwards, please do email me in my personal email, which I will include in the post-event communication to all of you. Well, have a great evening, and thank you all.
Thank you.
Thank you.